Chapter 7, Problem 62. A 250-gram block is dropped onto a relaxed vertical spring that has a spring constant of 2.5 newtons per centimeter. The block becomes attached to the spring and compresses the spring 12 centimeters before momentarily stopping. While the spring is being compressed, what work is done on the block by A, the gravitational force on it, and B, the spring force? What is the speed of the block just before it hits the spring? Assume that friction is negligible. And D, if the speed at impact is double, what is the maximum compression of the spring? So first we want to work on the block by gravity. And that's just the block compressing the spring to 12 centimeters, which would be 0.12 meters. So work by gravity is going to be the mass times gravity times the distance it's compressed, which is going to be equal to, the mass is 250 grams, which is going to be 0.250 kilograms times 9.8 meters per second square. And it's compressed 12 centimeters, which is 0.12 meters. And that's going to equal, it's equal to 0.294 joules. So that's the work done. And B is the work done by the spring force. So work by spring. And we know that that's going to equal U, which is going to equal minus 1/2 K. And since we're using D for X, D squared. And this is going to equal to minus 1/2. K is given to us as 2.5 newtons per centimeter, or 2.5 newtons for 0.01 meter, which ends up being 250 Newton meters, times, and D is given to us as to be 12 centimeters, which is 0.12 meters, and that is to be squared. So we got 0.12 meters squared, and that's going to equal a minus 1.8 joules. This is work done by the spring. So see, it says, what is the speed of the block just before it hits the spring? So now, since we have these difference essentially in potential energy in the form of work, we can set 1/2 mv squared is equal to 0.29 joules, we'll just drop the 4, minus 1.8 joules, and we'll solve for V. So this will go to quickly to V squared equals 2 times the difference. We may as well do our subtraction right now. And this should be a minus 1/2 mv squared. Get the direction right. So v squared is going to equal a minus 2 times the difference of 0.29 j minus 1.8 j, which is a minus 1.51. And this is divided by the mass, which is 2.250 kilograms. And this is going to go to V, velocity, equals the square root of minus 2 times the minus 1.51 divided by 0.250, and that's going to equal, it's going to equal 3.475 meters per second, which we're just going to call 3.5 meters per second. So that is what V is equal to. Then we go to part D. If the speed of impact is doubled, what is the maximum compression of the spring? So let's look at this formula. It's minus 1/2 the weight of the block doesn't change. It is times 0.250 kilograms. And if we double that, we're going to have 7, 3.5 and 3 is 7, and 7 squared is 49. So I know we're going to use a quadratic formula. I'm just setting it up. And we have the initial, which is mgd. So m is 0.250 times 9.8, that's gravity, times d. This is the work on the spring by gravity. But we don't know d now because we've doubled the velocity. And we have minus, which this is going to be the potential energy of the spring, which is going to be 1/2. We know the spring constant is 250 Newton meters, and it's x squared, which is going to be d squared. So 0, setting it up for the quadratic. 1/2 times 250 is 125 d squared, and that's minus. And this is 0.250 times 9.8, which is going to be a plus 2.45d. And when we bring this on the other side, this is going to be a plus, and the value of that is 6.13. So this is A, this is B, and this is C for our quadratic. We're going to multiply through by -1 in order to get this to be a plus. So we have 0 is equal to 125d squared minus 2.45d. This is the amount that we're trying to compress the spring, minus 6.13. Now, for the quadratic, D is going to equal a minus B. So a minus B and a minus will give us 2.45 plus, we're going to try this plus root, the square root of B squared minus 2.45 squared minus 4 times A, which is 125, times a minus C, which is a minus 6.13. And we're going to divide that all by 2a. And 2a is 250. And if you do the math on that, it's going to equal to 0.231 meters. So just to sum this real quick, we did the work of gravity, which was mgd, and that gave us a 0.294 joules. We did the work on the spring, which is minus 1/2 kd squared. The minus comes from the fact that the down was plus and the spring was trying to push back in the opposite direction up. So we have a minus 1/2 kd squared, and that gave us a minus 1.8 joules. We wanted the velocity, so we just set minus 1/2 mv squared, which is equal to the change in kinetic energy, which is the change in work, which was our 0.294 J and minus 1.8 J joules. And we solved for the velocity, and we got a velocity of 3.5 meters per second. And then the problem says double that and compute how much the spring compressed. So we doubled it. We went 1/2 using our mv squared times the mass. So double was 7. So 7 times 7 is 49. That's where we got that from. because I knew we had to use the quadratic, and I want to get all this on the same page. And this is the work done by gravity, which we've done before, times D. But we don't know D this time. It's not 12.12 meters because we doubled the velocity, minus the work done by the spring, which is 1/2 k d squared. We set up our quadratic and we solve for D using the quadratic. These are the values that we had to plug in. And D is equal to 0.231 meters.